Yeah. So now it's all done.
Okay. Thank you very much. Maybe actually let me first give an outline because I think maybe in the first time I just went into a proof and it was not clear exactly where we are going and what we are doing. So, okay. So firstly, we connected particle flows to probability flows, right? And in particular, what this means is that dxt equal to say vt dt plus square root 2 sigma t dbt is equivalent to del t pt is equal to minus grad dot vt pt plus sigma t square delta pt. Okay, this was the main thing that we proved the first lecture. Okay, so how are we going to use this? Okay, so then the second thing will be if I want to sample from P star proportional to say x power minus f, okay, then what should Vt be? Okay, and it turns out that the answer to this question is Vt is equal to minus grad f of xt. Okay, so in particular, what this means is that if we evolve according to dxt equal to minus grad f of xt dt plus square root t sigma t dbt, then P star proportional to x of minus f is the stationary distribution. Okay, this is the second result. Okay, so now how fast does this converge? Yeah, maybe sigma t is equal to 1. Let's say. So sigma t has to be equal to 1. Yeah, sorry. Yeah, yeah. Otherwise, you'll have some other point. Yeah, it will only stay dependent. Yeah, yeah. There is no dependence on time otherwise. Yeah. Okay. So how fast does xt converge in distribution to P star, right? P star is this probability distribution. So when I say proportional to, like when we integrate x of minus f, we will not get equal to 1. So we will just put a normalizing constant so that integral P star is equal to 1. So this is the flow-based method, right? Without noise. Yeah, I mean, we can use, I guess like that will require you grad log PT. So we had this flow-based equivalent that had a grad log PT. So here it only depends on the log density of the final target distribution. But the flow-based method will require you to compute log density of some intermediate things, which you currently don't have access to. That will be non-stationary as well, because like the velocity will actually depend on time. Like it's grad log PT and that depends on t, so it is non-stationary. I don't know if there is a stationary flow-based method, I'm not sure. I mean, there should be, because like you can take any like transport map maybe from like the Gaussian, whatever, initial distribution to the target distribution. Uh, yeah, I don't know actually how to make it like both only flow based and time homogeneous. I'm not sure if there exists one. Okay, so the third question then we will ask, now that we have at least some method which at least at infinite time will converge to whatever we want, then the natural question to ask is, how long does it take for it to converge, right? And you usually like there are results along this, but usually they require some kind of regularity on P star. And the kind of regularity that people assume on P star is that eventually it satisfies something called like log Sobolev inequality and so on. So that may be the one of the most general conditions. But for simplicity, let's say if F is mu strongly convex, okay, what this means is that for every x and y, we have that f of y is greater than or equal to f of x plus grad f of x with y minus x plus mu over 2 norm x minus y square, right? So under this condition, W2 square, this again Wasserstein distance. Maybe it's not super important what exactly it is now, but it's some measure of distance between probability distributions between Pt and P star goes down like exponentially fast, mu times t. Okay, so we have W2 square of P0 P star. Again, maybe I can just write what W2 square is. Between two probability distributions, PQ is expected value, sorry, min over gamma, such that gamma is a distribution over like two RD variables. So gamma restricted to X is mu, and gamma restricted to Y is equal to, sorry, P, and gamma restricted to Y is Q. Expected value under gamma X minus. So we want to have a like the best possible coupling between X and Y, where X comes from probability distribution P and Y comes from probability distribution Q. And what is the minimum distance squared that we can have here? And for now, maybe it suffices to say that W2 square of PQ is equal to 0 if and only if P is equal to Q. Okay. And what this says is that the distance between PT and P star goes down exponentially fast because like as T increases, so we are multiplying the initial distance by x of minus mu times T, right? So, okay, so this tells us that xt, like from the, so this is called the Langevin dynamics. So Langevin dynamics converges exponentially fast for strongly log concave distributions, right? Okay. In practice, maybe we are interested in sampling from densities which are not strongly log concave, right? So what do we do for that? So that's where the reverse diffusion aspect comes in. Okay. What this does is the following. So we, instead of starting from a random distribution and going towards the target distribution, we first start from the target distribution, because let's say we have some samples from the target distribution and we try to go towards random distribution. Okay. So let's start from target distribution and go towards say normal distribution, right? Like any distribution that we can easily sample from. Okay, so firstly, this is easy because normal distribution is one strongly convex, one strongly law concave, right? Because P normal of x is proportional to x of minus norm x squared divided by 2, right? So f of x here is half norm x squared, and this is strongly convex, right? So this is one strongly law concave. So we can directly apply the previous theorem, which says that the convergence to normal distribution happens very fast when we evolve it according to this thing, right? And in particular, so for this, the Langevin equation becomes dxt is equal to minus xt dt plus square root 2 dbt. Okay, right? And we know that this converges very fast to a random distribution, to the normal distribution. Okay. Now, what we want to be able to do is we want to use this process to learn things which will enable us to reverse this process. Because we know that the forward process has fast convergence, we know that the reverse process will also have fast convergence, right? And so what I'm saying is, so we start from P star, right? So we will do forward process, that's this, right? And you will converge to normal zero identity, right? What I said is this forward process converges very fast. So you don't have to take T to be like extremely large for this convergence to happen, because the target distribution, like which is a normal distribution here, is one strongly log concave, right? So this convergence guarantee that we just showed earlier, what that says is that this forward process converges extremely fast to the Gaussian distribution, right? If by some way we are able to reverse this process, right? So that if at time step t here we had a distribution pt, and somehow like we are able to reverse the process to also get like a distribution pt here, then the reverse convergence process will also be very fast. In the continuous time, it's straightforward to see, but when you have like approximation errors and so on, it's not straightforward, but like it's a proven result. But in the continuous time, we are just like time reversing. So you set like instead of t, you set like minus t, right? Yeah, we can do it, but usually we won't get, yeah, yeah, this is usually sufficient. I mean, the more strongly lock concave, like it will also become like sharper, and discretization might become a bit more difficult. But in continuous time, yeah, you can do that. But if you make it even more strongly, like I think like the discretization might be a bit more difficult. Yeah, like in continuous time, it doesn't matter. Oh, those I do not know, but you can put a constant to make it like even more strongly. Yeah, yeah. Let's, yeah. I mean, this is usually computationally fine. Like going beyond usually doesn't help too much. Like this is already like a constant time convergence, right? Okay. Okay. So the question is, how do we manage to reverse this process? So we have this forward process which converges to this one, and we now want to be able to reverse this process, right? Okay. So here we will use the following. So the forward process, let's say we had something like del T pt is equal to minus grad dot Vtpt plus sigma t square delta pt, right? Now, let's set qt is equal to p minus t, okay? then the question is, okay, so T here goes from 0 to minus, sorry, T goes from, yeah. So if you want to reverse this, we want P infinity to go to P0, right? Which is the same as Q minus infinity to go to Q0, right? Okay, so when we have this, what does it correspond to in terms of Qt? And that's the reversal equation. Okay, so del T Qt is equal to minus grad dot 2 grad log Qt minus V minus T Qt plus delta Qt. Does this make sense? So we have this forward equation, which tells us how the probability is evolving from t equal to 0 to t equal to infinity. And then we want to reverse it, right? And so we are making this notational change where we call Qt to be p minus t, right? And Q goes from minus infinity to 0, right? And then we want to understand, when we want to think of this reversal process, how is it evolving in time, right? And the evolution of equation of this, okay, so this equation again, like it's not very difficult. It's just setting like Qt equal to p minus t and then like just plowing through this first equation. What we get is that del t Qt is minus grad dot some quantity times Qt plus delta Qt. Okay. Yeah. Question? Yeah. 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 The dependency is coming from this grad log Qt here. So this were the gradients of intermediate, like score functions of intermediate distributions when we went from that particular target distribution to the Gaussian. So this is where we are telling it how to actually go back towards that exact same target distribution. Yeah, this Qt is p minus t. Yeah. Yeah. That's correct. Yeah, I'll. That's correct. Yeah. So this grad log Qt is the same as grad log p minus t. So the only so in order to implement this equation, the main thing. Okay, so this delta Qt is okay. Now, how do we implement it in a particle way, right? We again have this form where we have this velocity term and then a diffusion term. So what we should be doing is we should have dyt is equal to 2 grad log, I guess, as Rama said, we will make this p minus t minus v minus t dt plus square root 2 dbt. Okay. So if we are able to kind of implement this in the particle space, then it means that in the probability space, we are getting like this equation, right? And this is exactly reversing the original equation that we actually had, right? So if we are able to do this, then what we know is that y 0 is p star, because we started y minus infinity will be Gaussian, right? Does this make sense? Like this term is new here. Yeah, that's correct. Yeah. So the way we came from here to here is because like t we are reversing. This delta become so the delta, yeah. So the because of the change in the sign is why you have this extra 2 here. And then when we added this delta, like that's adding and subtracting. But even without that, you will have at least a 1. Like this 2, you can maybe you can remove the 2 and then like remove this component. but even without the two, like there will still be at least one term there. Yeah, 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 yeah. Yeah, so that's exactly the thing that I wanted to say here. So the forward thing will converge fast only if the target is one strongly lock concave. And yeah, yeah, yeah. So if you know that your target is going to be like strongly lock concave, then the like just doing Langevin dynamics converges very fast. But in general, your target might not uh, be strongly lock concave.
You are starting from normal and going to teach the multiple ways you can do that.
Yeah,
Among those, it will be very
this will converge very fast. I mean, there may be other ways, but at least Langevin dynamics will not converge very fast. And this is one way of making it converge faster. But at the same time, maybe we can say we are putting that hardness into somewhere else. We'll come where we are putting that hardness into, because sampling from non-strongly lock on or like uh, distributions that don't satisfy, say, LSI or yeah, log-Sobolev inequality is in general hard. So there are these general hardness results. Here we are sidestepping it because we are putting that hardness somewhere else, and we'll come to exactly where we are putting that hardness. But practically, it seems like putting hardness in that particular place and then solving it is empirically much better compared to dealing with this convergence hardness. So it's more of a practical solution to solving this problem. Theoretically, I don't know, like, yeah, yeah,
the amount you have F in example of it. But the gradient produces more error. Whereas the second method, you only need a sample from the inside to really slope it differently.
yeah. I mean, you still need to compute this grad log p minus t, and we will get to how to compute that, and that will be data driven. No, this one also you cannot simulate. Like you have to use the forward things and like the Tweedy's formula. Yeah, as long as you have samples, then you can simulate, and then you'll again have only samples there, but you want to use those samples to be able to compute this grad log p minus t. Yeah, you don't differentiate the data. Yeah. Uh, I mean, Dheeraj and Karthik, they have way to do also with discrete data, where they do more like uh, keep on forgetting names. Like if like in graphical model, for example, like you fix all the coordinates but one, and just conditionally sample that one, and yeah, yeah, yeah. Like mathematically, like this is very sim like elegant and nice to look at. Yeah. No, no, we'll not be doing any kernel density estimation. We'll be using neural networks or something to do like grad log p minus t estimation. That's where we will get to next. But it's not density, it's score function estimation. This is called the score. Yeah. So one thing I'm not sure if I think this is still an open problem, for example, is if I don't give you samples, I only give you access to this function f, where p star is proportional to x of minus f. Can you design a reverse like this kind of approach to sample in that setting? I do not know how to do that. I do not know how to sample that. And I think like that's still an open problem. So here we will be crucially using samples in order to estimate this grad log p minus t. So I don't know how to do this estimation without samples, but just directly giving access to like the target distribution's density or something like that. Yeah. Yeah, so you have two distributions and then you find the, that's a good point. Yeah, I don't know what the relation is. At least I'm not familiar with the relation between this and Schrodinger bridge. Here you are explicitly doing the noising. Yeah. Okay. Any other questions? Okay. Okay. So this is the reversal process, and what we know is that if we start from a standard normal distribution, then y0 will be distributed according to p star. So the only unknown at this point in being able to implement this algorithm is how do we compute this grad log p minus t, which is a score function of these intermediate things, right? So okay, so the way we do it is the okay. So this is another lemma we can prove, and this also goes by. So I think like this was originally maybe proved by Tweedy, and it's called Tweedy's formula. And what this says is grad log pt of x, where p was I think it, it's not updating. Yeah, sure. Sorry about that. Are there any other questions about what we're doing? Thank you. Okay, so what Tweedy's formula says is the following. So grad log pt of x, which is what we want to compute, is minus x minus to the minus 2. Does this make sense? Uh, So what we are saying is we had the initial target distribution and then we are denoising it to Gaussian distribution, right? And then we have these intermediate distributions indexed by t. So let's say we take the distribution pt at time step t. and we wanted to compute this grad log pt, which is called the score function of the distribution pt, right? And that is given by, at x, it's given by minus of this x minus e to the minus t times expected value of x0. So what was the starting point x0 if I were currently at x at time step t, right? And divided by 1 minus e to the minus 2t. So the good thing about this is that the only thing that we need to learn or estimate is this quantity here, which is the expected value of x0, given that at time step t I'm at x. And this we can easily do from samples by the noising process. Because what we can do is, let's say we have a neural network or whatever with parameters theta. So firstly, we will generate samples which are like x0, 1, at time step t, it will be xt1, and then it will be, say, until like we'll run it for, say, until times t equal to 1 or some large number, whatever, right? And then 1, and then we will have m such samples, right? Right? So these are given to us. I mean, originally only like these quantities are given to us, and all of the remaining ones we just get by noising them to the Gaussian distribution, right? Like the remaining things are all generated by us. But after generating, we do have these xt1 all the way up to xtm, right? Then we want to learn a neural network or some other model with parameters theta star, which is argmin over theta, right? 1 over m summation I equal to 1 to m and summation j equal to 1 to, sorry, uh, okay, let me, instead of 1, let me call this some very large number, k, right? So j equal to 1 to k or t equal to 1 to k. What we will do is minimize the norm of h theta of t xt I minus x0 I square, right? So what, yeah. So the claim is like with infinite samples, m going to infinity, h theta star of t comma x is approximating expected value of x0 given xt is equal to x. Does this make sense? So we have all these samples, and we are doing this minimization in this step to find the best parameters theta. And because we are trying to minimize the mean square error, what we will get will be the conditional expectation. And conditional expectation of what? So it will be the conditional expectation of x0, which is like the starting point. Given what is the thing that's given to us? We know that we are at time step t, and then the current value is this one, right? So h theta star of t comma x is going to be an approximation of expected value of x0 where we started from, given xt equal to x. Okay. So once we do this core function estimate, we have everything that we need to be able to implement the algorithm, right? So let me just recap everything and then write the algorithm. So, so the reverse diffusion sampling algorithm is the following. So we are given samples x01 all the way up to x0m. from some distribution C star, right? This is the only thing that we are given. Okay, so in the first step, we construct these noisy trajectories. Where we said dxt is equal to minus xt dt plus square root 2 dbt, right? And we can do this starting from like each of the samples that are given to us, and eventually like x for some very large t is roughly the standard Gaussian distribution, right? Yeah. 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 That's the normal distribution, right? So e to the minus half. Vt is minus xt. And sorry, p normal of x is proportional to x bar minus half norm x square. So the gradient of minus half norm x square is minus x. Okay. So for T large, we know that this will converge to this Gaussian distribution. Okay. So once we generate these samples, in particular, what do we have? Let's say we have, I mean, we will do this in discrete time. So let's say we will have x01, xt1, all the way up to some x capital T1, right? And similarly, we will have x0m, xtm, all the way up to x capital Tm, right? These are the trajectories that we have now after the noising step. Okay, so what is the second step? So we will do score function estimation. Right? And what does score function estimation do? We set theta star is equal to argmin over theta 1 over m summation I equal to 1 to m summation t equal to 1 to t or maybe 0 to t, 0 to t norm of h theta of t xti minus x0i square, right? And in particular, what will this do? So for large m, h theta of t comma x is roughly equal to the expected value of x0 given xt is equal to x, right? This is what we got from 3D's formula above. Okay, so now that we have this, what is the third step? So we implement the reverse process. What that means is that we will do dy t is equal to yt minus 2 yt minus e to the minus capital T minus little t h theta star of capital T minus little t yt divided by 1 minus e to the minus 2 t minus t dt plus square root 2 ddt. Okay. So all we are doing here is that in the yeah, so in the equation that we had here for the reverse yeah, in the reverse sampling, we had this 2 grad log p minus t minus v minus t. So v minus t was like minus x. So when we put minus and minus, we got a plus thing. And then this grad log p minus t, we use Tweedy's formula to put it, like relate it to the conditional expectation of x0, right? And then conditional expectation of x0, we are using this h theta star to actually approximate that. And when we put all of them together, this is the form we get. Okay. Yeah. So yeah, I mean, in practice, whatever, like M is usually very large, but in practice, like it seems like it's working quite well with whatever number of samples we're able to gather. Yeah. I don't know if it's lesser number. I mean, these models are trained on like extremely large number of images. Like we call M is yeah, quite large. Yeah. But I mean, compared to the dimension, would you say it is large or small? I don't know. Like the other thing is like we don't even know how to even think about these distributions like theoretically, right? Like what is the distribution of all images? What is the distribution of like all sequence of words? So yeah.
The result code for n going to infinity, I think that's really the result code for. But in practice, the amount of data that we are kind of using, samples that we're using, the number of n, is not that large, right? So I'm guessing that why does it hold in practice? Or why are we seeing the results?
Yeah, so I don't know an answer to that. That's an interesting question. Uh, but again, like we need to make this more quantitative. Like I don't even know how to make it quantitative. Like how I feel that like the number of samples is certainly not small, and like whether it's large or so this is also usually applied in what is called latent space. So that's called latent diffusion, where you don't apply in the pixel space of images. So you learn an encoder which encodes like images into a smaller dimensional space, and you do diffusion in that space, and then you'll use a decoder to decode the entire image from that space. So that space might still be not more than maybe 1,000 or few thousands. Whereas in the pixel space, yeah, if you have 100 cross 100, it'll be like more than 10,000 or whatever. Yeah. Mm. Yeah, I mean, it might depend on the problem also. Like what uh, the number of samples required for human faces might be different for number of samples required for like maybe cats or some other image data set and so on, right? So it does depend on the precise problem that you're solving. So yeah, there cannot maybe a general answer. Yeah.
So what TNX is there more important?
Yeah. So there is an analysis. So in particular, there is a paper by uh, maybe Chen, Chui, and like there are a lot of authors. So they do the discretization analysis as well as the approximation error analysis. So here, like all the things that we did is in continuous time. We did not account for like the discretization error. Then the other error that we need to account for is like how much error. So when we say this, like how much error can we accept and in what sense. And in particular, like what they say is like this error has to be in the PT square. Like if you have this, then they get a bound on like how these epsilon t's will add up to the final difference in distributions between, like I think like they get the KL divergence between the sample distribution at the end versus the true underlying distribution. Yeah. What I'm saying is like they get a bound in terms of all of these quantities. Then you have to see like what is the dominating term, and then maybe you spend more effort in reducing that. Yeah. But like at least the characterization, again, I don't know if it's a characterization, it's a bound. I don't know if it is tight or not, but they have a bound in terms of both the approximation error and the discretization error. And based on that, depending on the number of samples we have and so on, then you can say, is this discretization fine enough, or should I be doing even more discretization? Or maybe my approximation error is already so large that even if I do fine discretization, it might not really help much. So I should Yeah. So eventually, like you can maybe get only a argument in terms of epsilon t. And if you get more samples and use a larger network, hopefully epsilon t will be smaller. This is from few years ago, maybe 2022 or something. Yeah, yeah, Agni. Yeah, the good thing is like you don't need any assumptions. That's the main thing. You don't need, I mean, you don't need like law concavity or LSI or any of those conditions. The main assumption that's being, okay, so the hardness has to go somewhere else, right? Because like in general sampling is hard. So the hardness is actually going here. So what this says is that core function estimation might be very hard for some hard to sample from distributions. But in practice, maybe like core function estimation for whatever practical problems might not be very hard. So maybe like we're able to do a good job in doing score function estimation for like the space of images and so on. And that's why this is working. But this is certainly putting the hardness, taking the hardness away from sampling. Like in Langevin dynamics, the convergence was where the hardness was. Like it'll take very long to converge. It's taking the hardness from there. So now convergence certainly happens fast, only if you have like good score function estimates. So getting good score function estimates is where the problem might be hard. Yeah, if you assume that you are able to compute score functions in this good approximation in this sense, then everything else is computationally tractable. Okay, so this is about the, like this is the entire algorithm of like reverse diffusion process. So are there any questions here? Sorry, which minus t? T minus t? Oh, I guess we are sitting like qt is equal to p t minus t, because like t goes from 0 to t, right? So we are just so q also goes from the same. Yeah. So this is what we are using. Okay. So there are two things I can do. So one is I can again give like a brief explanation about like how flow-based algorithms work. So these are all diffusion-based algorithms. And after that, like depending on the time, I can maybe go over like the proofs of whichever components of these that might sound interesting. Uh, Let me just quickly first go over the flow-based thing so that like one has a complete picture, and then uh, I think applications wise, like this is a very general problem, right? So maybe I can say what latent diffusion is, but even before latent diffusion, so if you can think of these samples as just being some images, right? And we can implement like the rest of the algorithm. So what this will give us is a way to sample new data points from the distribution from which these x0, like the initial images were generated. So video generation. Okay, so before we go there, like I think there are these conditional generation approaches where, so conditional generation I'm also not very familiar with, but at least because like there are a lot more practical tweaks that people have to do to actually get them working. But from a conceptual point of view, this h theta of t given x, it need not be just dependent on like t and x, but will also be dependent on some other conditional. For example, if we type a prompt and then we want an image which actually corresponds to that prompt, then we would have like another conditioning variable here. And then that would basically be given xt equal to x and that conditioning equal to condition, right? So that way you can generate like these conditional samples. But this by itself usually doesn't work very well. So again, I'm not a practical expert on this, but I think first people learn the unconditional score functions like this. Then they also learn the conditional score functions, because the conditional score functions are usually much less accurate, because like we don't have conditionings for like everything, right? Whereas when we pool everything, like the unconditional one will be very accurate, but the conditional ones are usually not accurate. And then there are various heuristics which are called like score directed sampling and things like that. Core directed sampling, yeah.
For example, like images, I'm putting some condition, okay, certain three different backgrounds look like this. Maybe I get those kinds of pictures further change to get the condition image right. And then that's nice mathematical problem.
Yeah, can you repeat what you said,
I'm
please?
just saying that, no, I see what you said was very interesting, that I've trained on certain kind of images.
Yeah.
But now I'm putting conditions on them. I want to see trees in the background.
Yeah.
So you think there's a way of incorporating?
Yeah, there's a way. I mean, usually even in the training data, you have to have that.
Now I want condition on that. But that information to update the conditioning, you get a better job of saying it.
I mean, you have to be careful about overfitting, but
Still like mathematics.
yeah. I think like this core-directed sampling and conditional sampling, there is a lot of nice mathematics, I think, that will be required. Currently, it seems like a lot of these are still heuristics, and yeah, I don't fully understand those heuristics very well. Yeah. Yeah. Exponential of minus f. Yeah.
So are there other functions where you could use those things? Because I think you like it because you eventually get to normal distribution of things work out for you.
No, I think like grad log p somehow plays an important role in many places. So you take any probability function and you write grad log p, and if you think, yeah, it's just a parameterization maybe to make. Maybe another way to answer is you don't have to parameterize, you can just call it p. You don't have to write it as x of minus f, but eventually you'll end up with grad log p turns out to play an important role. You might as well give it a name, and I'm just calling it f, and then p will be, sorry, you'll give log p a name, which is f, and then p will be x power minus f. It's just like a naming convention, which makes like some of the, otherwise you'll have to write grad log p at a bunch of places. Otherwise you'll just write grad f. Yeah, and that's called the score function. So that's a important quantity for the probability distribution. Yeah. Yeah, it'll be discretized. Yeah, that's what I was telling Sandeep. So there are two errors. One is discretization error. The other one is approximation error in your conditional expectation. And this particular paper by Sitan Chen, Sino Chui, like that was the first paper which explicitly got a bound on the final convergence guarantee, meaning like the distance between the distribution that you get to and the target distribution in terms of both the discretization error and the approximation error. And there have been like further works which try to tighten the bounds further, but yeah, that's fine. So yeah, okay. So I think like for like 32 cross 32 or like smallish images, or even say, yeah, we can work directly on the pixel space. So this will be like 900, like I think this will be 1024, right? But if you go to like much larger images, let's say 512 cross 512 or something like that, like this will be much larger dimension. So what you do is you first learn an encoder. First learn like encoder decoder, right? What that means is you pass the image Okay, so you pass the image here, encoder, and then you will get a representation X. Maybe this will be only of order like R1024 or something like that. And then you will have a decoder. And then let's say you have image hat, reproduce, loss, minimize, right? So you use this to first learn an encoder and a decoder. And the encoder's job is to compress the image into much smaller dimension, which the decoder can later reconstruct, right? Now you would do like this sampling only on this X space. So you only generate a new X based on these all the X's for training that you have. And during generating new images, so you only generate a new X and then you pass it through the decoder, it will give you a new image. This is just a dimensional reduction technique. And yeah, usually you probably wouldn't go beyond a few thousands in the diffusion space. I think. Yeah. So this is called latent diffusion. Sorry. Mhm. Yeah, yeah. So I mean, at this point, you then like do everything in this latent dimension. You don't even need to care about like the original image or whatever. I mean, it will also depend on the probability distribution. Like even in 1,000 dimensions, like there could be some distributions which are hard to sample and some which might be easier to sample. Like some score functions might be easier to estimate and some other score functions might be harder, right? Yeah. Yeah, people, I mean, there are papers which have been trying to use diffusion based approaches even for language. And the main thing there is like language is discrete, whereas like these methods have been mostly successful on continuous time variables like images, things like that. So uh, I guess maybe images are the ones that I'm most familiar with, but anything which is continuous in nature, you can use them. Yeah, audio, yeah, you could potentially have audio diffusion models. Yeah. Okay, so let me, yeah, I'll now tell about, uh, there are different kind of approaches and computationally they can be faster and maybe recently like there's been more excitement and more work towards flow based methods because I mean diffusion methods were very popular because they were able to get like very high quality generations, and flow based methods also seem to be getting there, and it's certainly like a wide open research area and people are actively working on figuring out whether flow based methods, they are computationally efficient for sure. Can they also be as good as like the diffusion methods in terms of like sampling quality? So that's something people are working on. Okay, so let me talk about flow-based methods. Okay, so the main thing that we saw in the previous thing was this noising process, which kind of acted as an interpolation between the target distribution that we want to sample from and some easy to sample distribution, right? So let's say we have P0 and then we have P1, right? P1 is easy to sample from. and P0 is the target distribution, right? And what the diffusion approach did was it created an interpolation between P0 and P1, right? Which was given by this del TPT equal to minus grad dot whatever, right? So that's kind of an interpolation between P0 and P1 because it's a flow in the probability space starting at P0 and ending at P1. And there were some intermediate uh, points, right? So the question is, if we want to avoid the diffusion component, which is the noise component, are there other ways of creating easy interpolations between the target distribution and an easy to sample distribution so that we can execute the forward fairly simply, right? And it will converge fast. And at the same time, we want to be able to learn quantities that are important, which enable us to actually go in the reverse direction as well, so that we can sample from the easy distribution and then also generate samples, use that to generate samples from the target distribution, right? So let me give an example interpolation. So let's say we take x0 from p0 and x1 from p1, and I'll set xt is equal to 1 minus t times x0 plus t times x1 for t in 0, 1. Makes sense? So this is clearly, and if you look at uh, pt to be the distribution of xt, so this is clearly an interpolating path, right? So at t equal to 0, we are at p0, at t equal to 1, we are at p1, and this is some kind of interpolating path. Okay, so can we, I mean, this is just something that we just wrote, but we can pick whatever. And this we pick just because it's very simple, like it's just a straight line interpolation. Otherwise, like you can have some other curve that interpolates between them or whatever, right? So we can ask whether it is possible to uh, do sampling, sorry, reverse these kind of interpolations as opposed to the diffusion ones. And the nice thing about this is that this does not have any Brownian motion or noise here. Like this is just a simple interpolation between them, right? So for that, we again want to first convert like the particle flow. Like here, particles are flowing from x0 to x1, right? We want to convert this particle flow to a probability flow. And then the probability flow will tell us like how exactly the probabilities are evolving. And then it will also tell us what are the velocities that we need to take in order to get back, right? So for this, we have the following lemma. Okay, so the other thing to note about this is that this cannot be actually written as a velocity flow because this is not Markovian. Because like we are sampling x0 at a time t, if we are at some xt, I cannot write the velocity at the time just as a function of xt. It actually depends on like the entire path to be able to determine where it's going, right? So we cannot directly use the lemma that we previously proved, converting like particle velocity flows to probability flows. That does not directly apply here. So this needs a new treatment. And what this says is that, yeah, in practice, we will do discretization. But for yeah, we will do it many times. Practically, we will do discretization. But for conceptual thinking, we can just treat it as a continuous time thing. So it's not just 0 and 1. It's like the entire line between 0 and 1. Okay. So let's say we are given a distribution over flows. So these are no longer Markovian. So we have xt for t between 0 and 1 from some probability distribution where x0 comes from p0 and x1 comes from p1, right? Let pt denote the distribution of xt, right? Then we have the following. So del t pt, which is the probability evolution, is given by minus grad dot expected value of xt dot given xt times pt. Okay. Yeah, xt dot is like the velocity of uh, x at the time step t, right? And we are taking the conditional expectation of the velocity given that my particle at time t is at xt. So what is the condition? So this averages over like all possible initial conditions and then gets an effective velocity at the current point, right? So this now is a velocity field. Makes sense? So yeah, yeah, that's correct. Yeah, yeah. So this is now Markovian. So basically, the original thing was not Markovian because it depended on the entire path. It has a probability evolution flow, and that same probability evolution flow is also equivalent to this kind of velocity flow, which will now be Markovian. Except that we need to estimate this effective, like expected conditional expectation of the velocity at the given time, given that xt is currently equal to whatever x, right? And this again, okay, if you want to reverse it, again, like we will use the same thing. So now that we have written this probability flow, we can easily reverse it using just the same way we did the reverse diffusion thing. And the only thing that we will need to estimate again will be here this conditional this expectation, right? So okay. Okay. So now the flow based algorithm will be the following. So we are given x01 all the way up to, sorry, x0m from p0, right? And this is the target distribution. And we can also sample from some other easy distribution. Easy distribution, right? First, we construct trajectories. XTM, T in 0 to 1. We can use any kind of trajectory, that's up to us, right? And for simplicity, we can choose, we say choose XTM, XTI, so this will be I. XTI is 1 minus T, X0I plus T times X1I, right? Then we learn the velocities. This is the data-driven component. So theta star is equal to argmin over theta 1 over m summation I equal to 1 to m norm h theta of t xti minus xt dot. Okay. Yeah, P1 is a easy to sample distribution. Yeah, you can match any to any. You can like get more, like, yeah, you can get many more, like not just M. Yeah. But I mean, you have to be careful about overfitting, but yeah. Yeah, so you construct trajectories where you can match whatever, and then like this linear interpolation might be like one of the simplest things, right? Yeah, I mean, you're already constructing this trajectory, right? Like if in particular, like your xt is given by this, it's just like the velocity is a straight line. Yeah, we will come to the reversal thing now. Okay, so this is to learn the velocities, and like the reversal is just reversing the velocities. So we like during test time, we sample afresh y0 from P1, right? We sample from this easy to sample distribution, and then we do dyt is equal to minus h theta star. Yeah, they are constant velocity in some direction. Yeah, I learn the direction, but the direction will be, you need to take like a expectation over. There will be a dependence on t, because like this is this, like this conditional distribution could potentially have a dependence on t. Yeah. Yeah, I think like you will probably need some regularity conditions. Yeah, so you don't need like strong lock concavity or something like that, but I think like you do need some kind of smoothness of the distribution. Yeah, yeah, yeah. I guess like that will primarily come into the proof of this, like under what conditions on the paths and the target distribution like will we have this. Yeah, so we will have yt. So the claim is that if h theta star of 1 minus t yt is like a very good approximation of expected value of x0 given x uh, 1 minus t equal to yt, then y1 is like approximately being sampled from, sorry, the distribution of y1 is approximately equal to the target distribution. So we just have a velocity flow that took us from P0 to P1. We are learning those velocities in a data-driven manner, and then we are just reversing those velocities. And when we reverse those velocities and start from like the easy to sample distribution, we will end up at the target distribution P0. So yeah, of t and some x. Yeah. Yeah, it approximates the velocity. I mean, we are okay. So the sorry. So we want h theta star of t comma x to be equal to the expected value of the velocity x dot given x at time step t is equal to x. Uh, yeah, x dot doesn't depend on t, but this conditioning is basically what, no, I mean, it depends on the starting point and the initial and the final point. So let me write it clearly here. So Basically, you sample x0 from p0 and x1 from p1, right? And xt is equal to 1 minus t x0 plus t times x1, right? Uh, okay, so what is the expected value of x dot given xt is equal to x? This is equal to integral over uh, z, right? P0 of x, P0 of z, I guess, yeah. P0 of z, P1 of uh, x minus 1 minus t z divided by t times tz. So this is the probability that xt will be equal to x, right? And then we will have the velocity of this one will be what? Uh, x minus 1 minus t z divided by t. This is x1 minus z. Yeah, this will be the, yeah. Does this make sense? Okay, so there should be another, there is another summation. Thanks. Yeah. Yeah, maybe 0 to 1, like some discretization there. Does this make sense? Just because we have this conditional expectation is why we have this dependence on t as well. So that's all I wanted to cover. I can either, like, we can do one of the proofs of these things, or like yeah, we can stop here, or I don't think we'll be able to do any proof in that time. But if there are more questions, I'm happy to answer. Yes. So maybe another way to think about it is in Langevin dynamics, where we are saying like the convergence time could be very large for the distribution. The hardness comes during inference time, meaning that when you actually have to generate a sample, that's where the hardness is coming, right? You have to spend very long time to be able to actually generate that sample, right? Whereas here, you are putting all of that hardness into training because you already have a lot of data, and then you're writing this core function estimation. You can just do this entire thing offline before you want to generate even a single sample. But once you have this, generating new samples will be much faster, right? So you're putting a lot of this computational difficulty into training and ensuring that inference is very fast. Whereas like Langevin dynamics, inference time is where you will be spending a lot of time. And there is also, it's not clear how to even reuse all the effort that you put into like one-time sampling. So I have not personally done a lot here, but Dheeraj, okay, so maybe there are two works that I can mention here. So one, so Dheeraj Nagaraj has, actually he might be talking about this on Friday. Uh, so he developed like better discretization algorithms for reverse sampling. In particular, like people currently use what is called Euler-Maruyama discretization, whereas he recently developed a discretization that he calls Poisson midpoint method. based discretization. Okay, so this is one line. And then there is second work, which is on discrete diffusions. So how do you extend the idea of diffusion or noising and denoising for discrete distributions? Yeah, so they use something called, yeah, they develop something called Glauber generative models. Uh, yeah, and maybe like one when Dheeraj has a couple more directions, so maybe when he's here, I think it'll be good for people to talk to him and hear more from him directly. Yeah. So I think okay. So one problem again I don't know is all of these methods require access to samples from the target distribution. If I don't give access to the samples, but I only give you f where I want to sample from x of minus f, or like I give you the probability distribution function, but not samples from it, I don't know how to do these kind of methods in that particular setting. I think that's a important problem, and I don't know of how to do it. So all these approaches require access to samples from the target distribution. If I give you a probability density estimate of the target, so for a given x, I'll tell you what p of x is or grad log p of x is, but I will not tell you, like I'll not give you samples from that. So in that setting, I don't know how to do any of these approaches to sample from that kind of setting. So I feel that's an important open problem that I don't know how to solve yet. So usually I think like physicists and chemists, like especially I think in like this molecular energy search. So you want to find like low energy states, and that's where like these Langevin dynamics kind of approaches were originally invented and used quite heavily. So there you may not actually have samples, but you want to be able to find like low energy states and stable states and things like that. So you want to be able to sample from the Gibbs distribution. So there, like I don't know how to even apply these kind of methods. That may be also a computational issue, like yeah, I mean I don't know if they work or don't work, but I think like at least just computationally it becomes that people are doing, like this latent diffusion models are exactly what people are doing. Yeah. Okay, I think I'll stop. Thank you. Thank you.